Okay, let's talk about the last section of Chapter 4, which is mostly going to be dealing with tension, a little bit of air resistance, and then good old inclined planes, something you definitely have to be able to do. So tension, I will probably talk more about this in class and go over a couple examples. I've always thought tension was kind of a weird force. Tension is, if you look at this rope, this person's pulling on the rope with a certain amount of force, and the rope is transferring that force onto the box. So if the person pulls with 100 newtons of force, the tension in the rope, if the box isn't going anywhere, it's going to be 100 newtons. It's kind of strange because if you look at this last one, let's imagine, you just tie a rope to a wall and you pull with 100 newtons this way. Well, the wall is going to pull with 100 newtons that way. The tension in the rope is actually going to be 100 newtons. You might be tempted to think it's 0 because the forces cancel out, or maybe you think it's 200. In that case, it would actually be 100. Tension can also be weird when we talk about like pulley problems, especially we got someone pulling down like this, or if we have two masses hanging off a pulley and one's going up and one's going down. You might have to be able to figure out what the tension in the rope is. And it can be kind of a tricky little thing, and it would take me a few minutes to explain, so I'll probably just go ahead and do that in class as opposed to trying to do it right now. But we'll come back to that. So the force of tension. So here's an example problem with the force of tension. Basically, we're talking about a rope that supposedly is good up to 500 newtons, and we're trying to figure out if the rope might actually break in this case. So we got this 45 kilogram bucket, and we're going to try to lift it a certain distance and and have a final speed at the end. Obviously, what I'm trying to make you do here by saying it starts at rest, goes up 3 meters, and has 3 meters per second at the end, I'm trying to make you do an acceleration formula. So one thing to think about when we talk about tension, we're sort of talking about what I call elevator problems, which I think I've talked a little bit about before. Just remember that upward accelerations cause you to feel heavier. Upward accelerations cause more tension in a rope in the exact same way. So here, as we accelerate this bucket up, it's going to put more tension in the rope. So I don't know if I solved it mathematically the easiest way on this next slide. And again, I'm probably not going to really go through it. I'll let you go through it. But you could go through and figure this out. Do notice that one way or the other, I was going to have to figure out the acceleration of this bucket. Probably the easier way to solve this problem, and again, kind of talk to me in class, as you look at the way I solved it here, would be to solve for the acceleration first and see it's an upward acceleration of 1.5, and then add that to gravity. Take 9.81 plus 1.5, take that new gravity that the bucket is experiencing, so to speak, and multiply by the bucket's mass, and we will get the total tension in the rope at that point. You'll definitely do a few example problems with this as we go through. And let's see, this is just a components of force problem. So I think we've already talked about that one, so I really don't need that in here. So let's skip over to this. Air resistance. Air resistance, make sure you read through this. Air resistance is just air particles basically bouncing into you as you try to move through them. If you think of air as kind of like water, as you try to walk through water, the water will resist you. Air is kind of the same thing. It's these molecules that exist, and you're trying to push through them. It's going to try to stop you. So air resistance changes as you have more area, so the cross-sectional area increases. Air resistance increases as your velocity increases. As a result, you really need to use some calculus to do real air resistance problems, and I purposely wait and save that for one of the last things we do in the year, so you guys get really good at calculus. And frankly, it's a kind of a situation where I want you to sort of memorize the process, and I don't say that to you very often. So we're going to wait till the end of the year to do any real air resistance problems. But the chapter, it doesn't mention about it here, so I just kind of bring it up. Terminal velocity, that's when your gravitational force equals the upward force of air resistance. So of course, you don't stop moving, but you stop accelerating. And there's some terminal velocity, some objects. You obviously don't have to memorize those. And then if you get a chance, take a look at these slides, and it just talks about, how the elephant never really hits terminal velocity, where the feather hits terminal velocity very quickly. And then this just goes through and kind of shows that same thing. All right, so I want to spend most of my time here talking about angles and inclined planes. So I give you a little example problem here that we got some books that are attached to a rope, and then someone's pulling that rope at an angle. And then I give you a coefficient of friction, and I ask for the acceleration. So you've already done some of these friction type problems. What you need to realize in a problem like this is that the force of friction is still going to be equal to the coefficient times the normal force. But because this 90 newtons is being pulled at an upward angle, it has two components. It has a horizontal component that's going to try to move it down the hallway or whatever, but it has a vertical component. So that vertical component is actually going to reduce the normal force. Because if you could imagine this was, the whole floor was a scale, gravity's pushing these books down into the floor, but you're actually lifting them off the floor a little bit, not enough to actually pick them physically off the floor, but you're reducing the weight. The scale would read less. So to find normal force here, you would have to find the difference between the gravitational force and this y component. That would be your reduced normal force, which means it's actually going to reduce your force of friction. And so you'd have to consider that when you find the net force on the box to find the acceleration. So here I go through and I do that math for you. Notice where is the normal force here? The normal force looks like it's 45 newtons up. So the weight of the books was 196, but that means the normal force is only 151. That means the force friction is 75. The horizontal component, notice that's what we care about in terms of how fast the book's going to accelerate, is 77. So the net force horizontally parallel to the floor is 2.34. We can then use that to find our acceleration. All right, so that's one way to look at angles. The other, as I move my little joke thing out of the way, and try to get my slide back here. There we go. Is inclined planes. You definitely have to be able to deal with inclined planes. Typically, an object will just be sliding down an inclined plane. For some reason, I went like real hardcore on this example, so hopefully this doesn't mess with you too much. If this was just an object sliding down an inclined plane, we would probably just be we wouldn't really be looking at these vectors right here, but I made up a problem here where we have an object on an inclined plane that someone's pulling up an inclined plane at an angle. So they're pulling up with this yellow vector right here. So what I point out on this is a couple things. One, this downward vector right here is mass times gravity. So mass times gravity always acts straight down. Now as a result, this mass times gravity has a component that is perpendicular, that is perpendicular to the surface of the inclined plane, and it has a component that's parallel. We're going to need to find those. If nothing else was acting, so forget about this stuff right here real quick, this right here would be the normal force. The component of gravity that is perpendicular to the surface would be your normal force, if nothing else weird's going on. And more often than not, even on the AP test, that's probably going to be true. So if nothing else is going on, the normal force is equal to this perpendicular component. And then the force of gravity that's pulling you down the hill would be equal to this parallel component. Now here, because I decided to get crazy, this person's pulling at an angle up the hill, which means they have a component that's pulling the box parallel to the hill up the hill, and a component that's pulling off the hill. That would actually reduce the normal force, just like I showed you in the previous slide. From that, we could find the force friction. If this box actually is moving up the hill, then friction would act down the hill. If for some reason the upward pull wasn't enough in this box, even though we're pulling up the hill, is actually sliding down the hill, then friction would have to turn around and go the other way and pull up the hill. Because remember, friction would always oppose motion. All right, so let me go here. Here I just made up some numbers. And again, this is kind of a hardcore problem because of this part right here. But I said, let's say the inclined plane is 33 degrees. Let's say the mass is 11. Let's say that pulling force in green right there is 155 at 22 degrees. Relative, that 22 degrees is measured off of the inclined plane. So it would be right in that area right there. And the coefficient is 0.44. So then I just go about doing my work. I take mass times gravity as this vector here. I break it into its perpendicular and parallel components listed here. Try to color code all these things. The pulling forces, I had to break into theirs. Basically, I'm trying to get all of my forces to either be parallel to the hill or perpendicular to the hill. So I do all that and I net out my forces that are perpendicular to find my normal force. I use my normal force to find my force friction, and then I add up all my forces that are parallel to the hill. Once I get that net force parallel to the hill, I can divide it by the mass to get the acceleration. So an awful lot going on there, and certainly we'll look at some example problems with that one. Equilibrium, I can just say that pretty quick. Just remember, if an object's in equilibrium, it means all the forces that are acting on it add up to 0. So you could have 2, 3, 5, 10 forces acting on an object, and once you add up all the components of those forces, if they all add up to 0, the object's in equilibrium. If you're ever asked to find an equilibriant, that means the object's not currently in equilibrium, and they're asking you what one force could you add to it, so how many newtons and in what angle to put the object into equilibrium. And here I just show kind of a little problem that we got person A pulling on a box, person B pulling on a box, and I ask what is the equilibrium force. Well, what you do is you go out and figure out what the net force in the box is. So person A is pulling like this, B is pulling like that. I find their components. I find out that on the x-axis there's 112 newtons, on the y there's 54. That means there's 125 newtons acting at 26 degrees. So if you were person C, how would you have to pull to put this thing into equilibrium? You'd have to pull at the 125 newtons in the exact opposite direction, 180 degrees different, which would be 206. So I guess that is it. Again, I'll try to show you some of those pulley problems with the tension in class, and I'm sure we'll go over a few inclined plane problems just to kind of get you really used to those.